Hello everyone, welcome to AP Calculus. Today we are going to look at and recognize relative extrema using calculus, algebra, and graphic analysis. Let's get started. Now that you've completed your lesson preview, what you should notice is that there were no absolute maximums. The reason when you look at G, the point G is an open interval, and if there's an open interval, you don't actually touch that value, so no absolute maximum. Your absolute minimum does occur at A. Your relative maximums were both B and E, and your relative minimums were both C and D and F. Now, specifically, what I want you to notice is that your relative extrema occurred when your derivative was equal to 0 or where your derivative did not exist. So algebraically, whenever we're thinking about our functions and want to find relative mins and maxes, we're going to find the derivative, set them equal to 0, and figure out where they do not exist. So our definition, if we let f be defined on an interval I which contains c, f of c is the minimum if it is the smallest value on that interval, and it's the maximum if it's the largest value on that interval. Now these are called your absolute minimums and maximums or your global extrema. So both definitions or words are going to be used. For our extreme value theorem, so this is one that you need to put in your repertoire, if f is continuous on that closed interval, then f has both a minimum and a maximum. You are guaranteed the minimum and maximum. Those extreme values will occur where your derivative is equal to 0, where your derivative does not exist, or they will occur on the endpoints. So in order to find the absolute extrema, you will check the values at 0, where the derivative is 0, where the derivative does not exist, and those endpoints. Relative extrema, though, that's where you have a point at its highest on either an open or a closed interval. So you have a relative maximum, or you could have a relative minimum. Now, the relative maximums and minimum are also called local extrema. They occur where your derivative is equal to 0 or where your derivative does not exist. We do not need to check the endpoints when we're looking for relative extrema. So graphically, when we take a look at our pictures, you want to find the relative extrema. So the relative extrema, when we look at it, you can see that the relative extrema is the y value, and that y value is 2. Now, if you're asked to give the point, it would be 3, 2. Now notice it's where your function went from increasing and then began to decrease. So relative maximum will occur where your function changes from increasing to decreasing. For a relative minimum, your function is going to be the lowest point on an open or closed interval. It's the y value again. So the y value or relative extrema will occur when y is equal to 0 or at the point 0, 0. Notice that this is where your function is decreasing and then switches to become an increasing function. So a relative minimum is where f of x changes from decreasing to increasing. It has to make that change in order to be a relative min or max. Now, it is possible to have both a relative min and max as we look at this trig function. You notice you have a relative max at the point pi over 2, 1, and you have a relative min at the point 3 pi over 2, comma, negative 1. Now notice again, your relative max was increasing and then began decreasing, and your relative min was also decreasing and then increasing. So if we were to make a value of sign chart, here's your f of x. At the point pi over 2, what is f of x doing? It is increasing and then it decreases. And then at 3 pi over 2, you will start to increase again. But you also have information about f prime of x. F prime of x is negative. Excuse me, it's actually positive. Let's erase that. F prime of x is positive, and then negative, and then positive. So we're going to use the derivatives to tell where the function is increasing and decreasing, and that will also tell us where our relative mins and relative maxes will occur. So algebraically, how do we find the extrema? We will determine f prime of x. Once we determine f prime of x, we want to know where f prime of x is equal to 0 or where f prime of x does not exist. So we want to determine where f prime of x equals 0 or where f prime of x does not exist. So those are the two values that we can find an extrema. Afterwards, we're going to need to find the f of x value. So we're going to make a table to determine f of whatever value we have for the first derivative equals 0 or the derivative does not exist. So we actually want to know which values of f of x are largest or smallest. So if we're looking for the relative extrema, that will be good enough. However, if we want the absolute extrema, we also need to check the endpoints. Because remember, the absolute extrema can occur at endpoints, and they do not have to be the relative extrema. They could be, but they don't have to be. So these values where your derivative is equal to 0 or is not differentiable, they are called critical numbers. And you can see that where your critical number does not exist, you're going to have some sort of cusp or corner on the graph. And if your derivative is equal to 0, that's of course where you have your horizontal tangent line. So if either of these two things are occurring for your function f of x, then c is a critical number of f. So we could have simplified these set of directions and said, find the critical numbers. And once we have the critical numbers, those critical numbers are going to help us determine where the extrema occur. For our first example, we're going to use these ideas to find the extrema of f of x over the interval. And in order to find the extrema, we first find our derivative, f prime of x, equals 2 minus 2x to the negative 1/3. Since we need to figure out our critical numbers, we're going to multiply this by x to the 1/3 over x to the 1/3 in order to find a simplified version of f prime of x. So f prime of x, once we multiply, is equal to 2x to the 1/3 minus 2, all divided by x to the 1/3. When we determine our critical numbers, we want to know where f prime of x is going to be equal to 0. So we take 2x to the 1/3 minus 2, set it equal to 0, and we know that x is equal to 1. Then we want to know, where does f prime of x not exist? Look at your denominator. We have x equals 0 as one of the places where your denominator is equal to 0. Now, if we look at the original function, 0 is in the domain. So we do need to include 0 as one of our critical numbers. But you should always check your domain when you are given your critical numbers, or determine your critical numbers. Next, we want to find our extrema. In order to do that, we're going to make a table of values. The absolute extrema are the largest and smallest y values on your closed interval. And in this problem, we're going to substitute the critical numbers in 0, 1, which are both on our given interval. as well as the endpoints, -1 and 3. We're substituting into f of x because we're looking for the largest and smallest values of f of x. And for 3, we have 6 minus 3, f divided by 3. After making your table of values, it's time to analyze which y value is the largest and which y value is the smallest. So for our absolute maximum, you're going to state that the absolute maximum occurs where you have f at 0 equal to 0. And then for your absolute minimum, you're going to make a statement that the absolute minimum occurs where f at -1 is equal to -5. So the table of values is an approved method for showing the absolute mins and maxes, but you still need to make the statements once you're finished. For example 3, we're going to find the extrema on an interval that is not closed. So this is going to allow us to use limit ideas within our problem. Find your derivative, g prime of x equals, and you have the bottom, times the derivative of the top minus the top, times the derivative of the bottom over the bottom squared. So we used our quotient rule. Simplify the problem. This is going to end up becoming your x squared minus 2x divided by your x minus 1 squared. So this problem is easy to see our zeros. Factor just a little bit more. We have x times x minus 2 over x minus 1 quantity squared. So for our critical numbers, let's determine where g prime of x is equal to 0. And that would happen when x equals 0 and x equals 2. Next, we're going to determine where g prime of x does not exist. Remember, where your derivative does not exist is where you might have a cusp or a corner. Our derivative does not exist at x equals 1. However, this is not in your domain. So we will not include x equals 1 in our table of values. It is not a critical number if it's not in your domain. Now, as we look more closely, we notice that we're going from -1.5 to 10. So when you make your table of values, your x and your g of x, as we look at our table of values, notice 0 is not in your domain. So we are not going to include 0 in our table. We have our critical number 2, and we have the endpoint. We don't include 1.5, so keep that in mind as we're looking at the y values. Substitute the 2 into g of x. We come up with 4. Substitute your 1.5 in for g of x, we come up with 4.5, but remember, we're not actually touching that 4.5. When you substitute your 10, you get 100 over 9. So we need to determine our absolute max and our absolute min. As long as the endpoint 1.5 with 4.5 is not being used, then you can say that f at 10 is equal to, for the maximum, 100 over 9. And the absolute minimum, f at 2, is going to be equal to 4. Had for some reason the 4.5 been smaller, let's say 3.9, you would write that there was no absolute minimum because, well, you're not allowed to touch that point. It's time for you to stop the video and try questions numbers 1 and 2. And mine has a typo. The endpoints are going from 0 to 2 pi. If you need to make that correction, please do. I chose example 4 because, as you can see, it's a bit more complex to find the derivative. Let's begin with a product rule. Your h prime of x is going to be equal to first times the derivative of the second, which is your 2/3, x minus 1 to the negative 1/3, plus the second, x minus 1 to the 2/3, times the derivative of the first, 2 times x plus 3 when you use your chain rule. All right, so this complex problem needs to be simplified. And in order to simplify it, we're going to multiply by x minus 1 to the 1/3. That'll cancel out your negative exponent over x minus 1 to the 1/3. And then, of course, we should also multiply it by 3/3 to clear your fractions. Simplify some more. We're going to be left with the quantity x plus 3 squared times 2. Notice your x minus 1 to the negative 1/3 cancels out, plus the quantity x minus 1 to the first power times 2 and 3 is 6. And then we still have x plus 3 in the numerator divided by your 3 times x minus 1 to the 1/3. All right, now, of course, we need to do some simplifying by factoring. We're going to have x plus 3 multiplied by 2, and our remaining terms will be x plus 3 plus our x minus 1 multiplied by 3. In your denominator, you still have 3 times x minus 1 to the 1/3. Simplify just a little bit more. 2x plus 3 times our quantity. We get a 2x in your numerator times 2 will eventually become a 4x, but 2x for now. All divided by our denominator, which is 3x minus 1 to the 1/3. So now that we've simplified this function, you can see that you have critical numbers where your derivative is equal to 0. So that will be at x equals negative 3 and x equals 0. You also have critical numbers where your derivative does not exist, and that will be at x equals 1. We're going to make our table of values to determine the mins and maxes. This is your extreme value theorem. So whenever you're looking for your extrema, you're using your extreme value theorem. Place your critical numbers in your table. You've got 1, 0, negative 3. All of those numbers are on your interval. Keep an eye on the interval. Put the interval into your table. We have negative 4 and 5, but remember, we're not actually going to touch the 5. These problems are non-calculator problems, so practice doing your substitution without a calculator. 1 gives you 0, negative 3 gives you 0 when you substitute. 0 is 9. Then we will have negative 4 is 5 and 2/3. And of course, 5 is 64 times 4 to the 2/3, which is the largest number in your table, but you're not actually allowed to touch it. So for your absolute maximum, the maximum could have occurred at 5, but you're not touching the value of 5. So the absolute maximum does not exist because it is not in the domain. Your absolute minimum is going to be f at 1, which also equals f at negative 3, and that value is 0. So when you're looking for an absolute min or absolute max, remember that is the y value of the function. I just like to write f at the value 1 so that we know where it occurs. For example 5, you are asked to find the extrema of a piecewise function. So you've had enough experience with these to know that the function might not be continuous where the endpoints are connecting. So we're going to look specifically at 2 as we find the derivative. So j prime of x is going to be equal to, in pieces, 2 over, 2 or 2x minus 5, depending on which interval we are looking at. And next we want to think about those critical numbers. Was the function continuous? When we found the limit as j approaches 2 from the left. 2 from the left is using the interval 0 less than or equal to x less than or equal to 2. The answer is 3. As x approaches 2 from the right for j of x, you also get 3. So it is continuous, but is j prime of x continuous? If it's not, that's fine, because we know that the critical numbers occur where your derivative equals 0 or does not exist. So let's look at where j prime of x equals 0 first. It could equal 0 when 2x minus 5 equals 0, or x equals 5 over 2. Now that is on the interval, so it is a critical number. But where does j prime of x not exist? Again, we're going to do a limit as x approaches 2 from the left of our j of x. This time j prime of x. 2 from the left is 2. And then we take the limit as x approaches 2 from the right of j prime of x. And in that case, the answer is going to be -1. So we do have a second critical number, and that critical number occurs when x is equal to 2. So applying extreme value theorem, place your values in a table. The critical numbers that we include are going to be 5 over 2, 2, and now the endpoints. The endpoints we get from the piecewise function. We know we're starting at 0 and we're ending at 3. Do your substitution. You have an 11 over 4, 3, put your 0 in, you get -1, put your 3 in, you get 3. And that tells us we have an absolute maximum, according to the extreme value theorem, at j at 2 equals 3, and an absolute minimum for j at 0 equals -1. For today's lesson practice, make certain that you definitely practice finding derivatives, setting those equal to 0, and figuring out where your derivatives do not exist. So take a look at the questions that I provided, and you have a fabulous day.